All right, let's dive into a really beautiful piece of work today. Michael Bird's paper 36. This paper managed to solve a major mystery in the non-holomorphic fractal series. We're talking about something called multi-kernel universality, and let me tell you, the proof they came up with is just elegant. So, let's get into it. So, here's our game plan. Think of it like we're following a mathematical detective story. We'll start with a mystery, uncover the brilliant idea that cracks the whole case wide open, check all the evidence, and then get to that triumphant final solution.
Okay, so first up, the universality conjecture. To really get why paper 36 is such a big deal, we need a little backstory. We have to look at the clues that the previous papers left behind, because they set the stage for a pretty tantalizing, but totally unsolved mystery. Right, so this whole thing builds over a few papers. Paper 32 gave us these really strong hints from computer simulations. It showed that three totally different mathematical objects, these things called the WBA, Lorentzian, and Approxian kernels, all seem to behave in the exact same way. They all landed in something called the Watson band. So paper 33 comes along and says, hey, this probably isn't a coincidence, and they formally state a conjecture. This has to be a universal thing. But then the big breakthrough in paper 35, well, it was a full, unconditional proof of this rigidity, but it only worked for one of them, the WBA kernel. The huge question was still hanging out there. Can you prove it for all of them? And that brings us right to the heart of the problem, proving this conjecture. The whole goal was to go from one specific example to a universal truth that covers an entire class of these things. This is the mystery that paper 36 set out to solve. So how do you even approach that? Do you just suffer through the incredibly difficult proof from paper 35 all over again for the Lorentzian kernel, and then a third time for the abelian kernel? Well, the brilliant move in paper 36 was to say, no way, there's a much smarter way. Instead of crafting a different key for every single lock, what if you could design one master key that opens them all?
So what is this master key? It's this, the admissible Watson class, which we'll just call K. And what's so amazing here is how simple it is. This class isn't defined by some long, complicated list of rules. It's just one single, clean condition. The function's maximum absolute value, its supremum, has to be less than or equal to 1/2. That's it. That's the whole definition.
Okay, so the million-dollar question is, do our three kernels actually fit in this class? And the answer is a huge, resounding yes. The WBA and Lorentzian kernels, they push right up against that 1/2 limit, hitting it exactly at their boundaries. And the alien kernel? Its max value is around 0.4289, so it fits comfortably inside. All three of them, they're all members of this one unifying class. And this is the moment where everything just clicks into place. It's the most powerful insight in the whole paper. Remember that super technical, difficult Lasota-Yorke proof from paper 34? It turns out that proof never, ever cared about the specific shape of the WBA kernel. The only thing it ever used was that supremum bound of 1/2. So here's the kicker. You can swap out the WBA kernel with any function from that entire class K, and the proof, the constants, all of it, it just holds. It was a universal proof the entire time, and they just hadn't seen it yet. It is an absolutely incredible realization.
Okay, so that is just massive. But what about the pressure bridge? That was the hardest, most complicated piece of the last paper. Surely that part has to be rebuilt from the ground up for each new kernel, right?
You'd think so, but no. It generalizes with basically zero extra work. The logic is so robust, it holds for any function h in our class K. First, you express the key coefficients in a way that doesn't depend on the kernel's shape at all. Then, you apply this powerful tool called the RPF theorem, which only needs that same supremum bound we keep talking about. And finally, you use another formula to connect it all to the spectral radius. The entire bridge is solid for the whole class. Now, if you're really sharp, you might be thinking, wait a minute, the Lorentzian kernel isn't an odd function like the others, doesn't that matter? And it's a great question, but the answer is no. The proof very cleverly sidesteps that whole issue because it relies on the absolute value of the coefficients. Plus, this underlying weight that gets used in the math, this e to the epsilon h term, is always positive anyway, no matter if h is positive or negative. The whole thing is just really solid. So the abstract theory is beautifully general, but you've got to connect it to reality with some hard numbers, right? It all relies on these computer-assisted proofs finding a spectral gap.
And since those have to be run for each specific kernel, how did they handle that?
Well, they didn't have to reinvent the wheel, which was pretty smart. They just created 2 new scripts, one for the Lorentzian kernel and one for the alien. But they used the exact same proven 2-stage architecture from paper 35. Stage 1 is a quick and dirty check using Monte Carlo simulation, and then stage 2 comes in with super high precision math to give a rigorous, certified, ironclad result.
And here are the receipts. This table is the hard evidence. You can see all 9 combinations. Our 3 kernels, each tested at 3 different values of this parameter, epsilon. And look down that last column. In every single case, the certified spectral gap is positive, a check mark all the way down. This is the concrete proof you need to make the whole theory work.
Okay, so we've got the elegant, general theory, and we have the specific, computer-certified results. How do these final pieces lock together to close the book on this conjecture, once and for all?
The last piece of the puzzle is this idea called uniform KL persistence. It's basically a stability result. And what it says is that the stability of that spectral gap we just found, it only depends on that same old supremum bound of 1/2. And since that bound is the same for every function in our class K, it means the proven rigidity window of validity applies to all of our kernels at the same time. It's one window, one proof for everything.
Which brings us to the main theorem. This is where it all comes together. For all 3 of our kernels, and for any epsilon in that rigidity window, number 1, we know a certified positive spectral gap exists. Number 2, we know their exponential type lands right inside the Watson band. And number 3, that Watson band is totally separate from another region called the orbit band. It's a clean, comprehensive victory on all fronts.
And with that, the story reaches its climax. Watson-Van rigidity is no longer just a conditional result for one lonely kernel, it's an unconditional theorem for all 3 of them. The long-standing conjecture 33.3 is officially closed. Done. So, the case is closed, but you know how it is in math and science. Closing one door just reveals a whole new set of doors to open. So let's take a final look at what's been accomplished and what mysteries might be waiting for us next. This scorecard really sums it up perfectly. Lasota-Yorke, the pressure bridge, KL persistence, Watson band rigidity, all unconditional theorems now. The specific gaps are certified. The conjecture is closed. But just look at that last line. The question of enlarging that rigidity window is still wide open. And that just leaves us with the next really tantalizing question. We've proven rigidity on this interval from 0.84 to 0.90. But how wide can that window really get? Can we push it further? And what's so cool is that thanks to the beautiful abstract framework built in paper 36, all we need is a new, wider computer certification. The general theory is already there, ready and waiting. And that, my friends, sets the stage perfectly for paper 37.